How's it going, AS Math? It's Mr. Knight, and we're going to continue on with delving deeper and deeper and deeper into the catacombs of graphing. We're going to look at max and min points today with derivatives and kind of see how those guys are related, and talk a little bit about increasing versus decreasing functions and how we can determine that with our gradient functions. So below we have two graphs here on either side. I apologize if they're a little like this guy is kind of messed up. I was doing this in a car. I wasn't driving, but that didn't make it any easier. But we have these two graphs, both parabolas, and this guy is going to be opening down. It's got a maximum at 0, 16. If you plug in 0 into x, you'll find that your y value is 16. And over here, we have a minimum at 0, negative 16 right there. So how are those guys in derivatives actually related? So first of all, we call max and min points stationary points, just because they are neither increasing or decreasing. They are stationary, okay? They are just chilling right here and here. And there's a couple features of stationary points. This is the connection to derivatives right here. dy dx is equal to 0 right there. If you look at the gradient of our tangent lines going through those stationary points, yeah, that's a slope of 0 right there, and it's always a slope of 0. Now for maximum points, so like this guy on the left-hand side, the gradient, if we think about a bunch of tangent lines being plotted along this for every single point, the gradient ends up being positive up to that stationary point, and then it starts being negative to the right of it. So depending on what the sign of our gradient is, we can actually determine the nature of our stationary points, whether they're maximum or minimums, because this just tells us if it's a stationary point. It doesn't specify it's a max or a min. That's where this guy will come in. And similarly, it works with the minimum too, except if we're on the left-hand side of our stationary point, you could see that the slopes are all going to be negative, and then it's going to be 0 at the stationary point, and then it's going to be positive to the right of that as well. Okay, so let's see how those will work in the context of some problems. Okay. Here's example 1. Something you would see on your homework typically would be something like this. Find the stationary points on the given curve and then sketch the curve. Okay. So the first thing we got to do right off the bat for finding the stationary points is I got to find the derivative of this guy. Now if I sketched it, I could probably find the max and min, but sketching it would take forever. The derivative is way quicker, because I know I could take the derivative of this guy using my power rule, and I get 3x squared minus 3. And then I know the derivative is 0 at stationary points, so to find them, I'm just going to plug 0 in for dy dx, and then I'm going to solve for my x values. And I find out that x is equal to 1 or x is equal to negative 1. Those are my stationary point x values. So if I wanted to find the actual points, I could take those x values, I could plug them back into my original curve, and I'll get my y values out of that. And we'll do that in a bit. But first we got to figure out what type of stationary points these guys are at. Are they maxes or are they mins? Okay. Well, back to what I was saying earlier when we were looking at, oh, is it a max or a min? We can plug values in on either side of the stationary point. The sign of the gradient function is what's going to determine if it's a max or a min. So if I have x equals negative 1, I know that's a stationary point, like where that occurs. I'm going to plug in x values to the left and right. So I'm going to plug in negative 2 into my slope equation, and I'm going to end up getting a positive 9 out of that guy. So to the left of it, it's positive, and to the right of it, when x equals 0, I get negative 3. So it's positive on the left, and it's negative on the right. So for you guys, it's going to be, I don't know how I'm going to orient to this, but it's going to the left, it's going up, 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 and then it's to my stationary point, and then it's going to start dipping down. It's going to have a negative slope, okay? So that just screams out maximum. So at x equals -1, that's where a maximum point is. And you can see it. You could see it for the other stationary point. If I do a point to the left, we already got x equals 0, and a point to the right, I know that's a +9 after I plug it in. So it's going negative, stationary, and then it's positive for my gradient, so that's a minimum right there, okay? So using that, it helps out quite a bit. And now we can find those points. I can find points from the x values. I'm going to plug in 1, -1 back into the original curve. And when I do that, I end up getting -1, 3 for my maximum, and for my minimum, it's 1, -1. And if I go ahead and sketch this, it won't be too bad actually. I'll sketch it real quick. I'm actually looking for a pen right now as we speak. If I go and I sketch this, I know where the max and mins are, and I know this is a cubic function. So the cubic function is going to look something like that. You can also make an XY table, but just knowing that gets me pretty far, because I know, let's see, -1, let's see, 1, 2, 3, +1, -1. So at -1, 3 is right up here. +1, -1 is down here. So I know there's a max here, a min here, and I know it does one of these guys. So it's going to come up like this. It's going to dip back down. It's going to go back up like this. And that's a pretty, I mean, it's a rough sketch, but it's a sketch. And that guy's done. Okay. So that's really what it comes down to, is setting dy dx equal to 0, and then plugging in some test points to the left and right, kind of like with inequalities, if you remember that from way back when. We're going to try it again with this guy. Alright, we're going to find stationary points for this curve and determine their nature. And when it says determine their nature, it just means, is it a max or is it a min? Okay. So I find my derivative of this guy. And now I'm going to set dy dt equal to 0, because that'll help me find my t values where I get stationary points. And when I do this, I factor out a 2t, and then I use the difference of 2 squares for this guy to factor that guy out further, and I end up getting these 3 factors. I set them all equal to 0, and I find out that t is equal to these 3 x values, or t values actually. Okay, so once again, I want to figure out what type of stationary points those guys are. So again, I can put points to the left, to the right. What might be handy is a table like this. Okay, and I recommend you do this on your homework, especially when you are dealing with like stationary points that are closer together, like this one. They're very close. Okay, but yeah, so we just have the sign of dy dt, whether it's a minus, positive, or if it's stationary, it's going to be 0. And then for the stationary points, so like here, here, and here, I'm going to write down if it's a max or a min, just based off what the sign is. And I went ahead, I already plugged in some just test values. So like for this one, I plugged in like -1, and I found out the value for that guy when I plugged it into my gradient function back up here. When I plugged in -1, I ended up getting a negative value for my dy dt. Similarly, when I plugged in something that was between -0.5 and 0, my 2 stationary points, again, I found that when I plugged that value in here, it was positive. Okay, so just by looking at that, this stationary point right here, to the left of it, it's negative, and then it's going positive, so it's a minimum. It's a positive for here, and then it's going to dip down to minimum, so I know this guy is a maximum. And likewise here, it's going down, then up, so it's a minimum as well. Okay. So then I can plug those t values in, the -0.5, 0, and +0.5, back into the original curve equation. Now I'm going to get those y values, and that is what I end up getting for my values. The 0, 1 was a max, and these guys were mins. and that guy's done. Okay, you can even see it on Desmos, right? This was on my original curve, and you can see I got my two mins right here, and I got this max right here. It looks kind of weird because everything is super duper close to each other, just like that, which is why the table was actually very handy in this case. Okay, comparing that to the gradient function, yeah, when dy dx is 0, like here, 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 when the y value is 0 for it, the dy dt, that's what that is. That's the y value here. You can see it corresponds to the maxes and mins of our original curve, which is kind of interesting, but it makes sense of what we're doing algebraically as well. All right, or calculatusly. I'm just going to stop. Okay, increasing and decreasing functions. Two quick rules, and we've seen it already. When dy dx is greater than 0, when we have a positive slope, it's increasing. When it's got a negative slope, it's decreasing. Okay, so you might see something like this. It says, show that, we love these problems, show that y equals x cubed plus x is an increasing function. Let's take the derivative of that guy. Let's get 3x squared plus 1. And so if we try to find out, okay, when we got to find that dy dx is positive, right? It's, you know, when it's greater than 0. Okay, this is pretty much the answer. Since x squared is just going to be greater than or equal to 0 for all values of x, dy dx is greater than 1. That guy's done. Yeah, let's see it graphically because that probably makes more sense. This is our original curve, and you can see it's got a positive slope pretty much throughout the entire thing. And it doesn't really matter what I plug in for x. I'm always going to be increasing along this, and dy dx function kind of showed us that. Doesn't matter what I plug into this guy, I'm going to have a positive value, which is kind of sweet. So it's an increasing function. And finally, example 4, find the range of values of x for which the function y equals x squared minus 6x is a decreasing function. Okay, so this is going the other way. First of all, we got to find dy dx. Again, we find that it's 2x minus 6. And we want to know if it's, or for which values of x this guy is a decreasing function. So I have to make it so dy dx is less than 0. So this is my dy dx. I'm going to make it less than 0. Okay, and that's actually what I end up getting right here. Okay, I just solve for those x values, and I find that when x is less than 3, then we have a decreasing function. And once again, Desmos. Hello, how's it going? We are looking at this guy, and yeah, you can see this is our original curve. When x is less than 3, so this way, it's a decreasing function. The slope of this guy is going down, 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 stationary point, and then going back up. Okay, so it actually makes sense based off our answer. This is Mr. Knight signing off. Have a good day.